Okay, so we are here. We are going to talk today about uh, mostly about the properties of the liquid surface. Uh, this is a picture of what will happen if we will drop an object on the surface of the liquid, and you can see this beautiful pattern of waves propagating from the center to which this force was applied. And these kinds of waves are called capillary waves, and they played a very important role in many engineering and technical applications. But before we start talking about them, let's first think for a while about what are the properties of the liquid-vapor interface. This is the kind of a picture. We have a liquid, and above the liquid, if the liquid is put in the container which is in the gravitation field, that is easy to see the situation, that the liquid which is heavier is on the bottom and the vapor which is lighter is on the top. And the region in between the liquid and vapor is called the liquid-vapor interface. When we will take a microscope and look up very closely at what is happening here, we will see that we have a lot of particles in a denser phase of the system that is liquid. And when we will look it up, we will have less dense region filled up by the same molecules, but there's less of them per unit volume than in the liquid. So if I measure a density of the system, that is how many particles there are in a given gauge volume, then if I plot it along the axis vertical, then I get the picture like something like this. I have a higher density phase, and I can always use the unit such that the density of a denser phase is equal to 1, that is on this drawing. And then on top I have a lighter phase, and the density is having a very nice profile. And that profile is something which those of you who learn a little bit about the trigonometry might recognize as the hyperbolic tangent function. And in fact, that was a very cute observation of Mr. van der Waals 140 years ago or so. Then he realized that he can actually prove within the model of a liquid, which is called the van der Waals model, that the region of a density in between the liquid and the vapor is actually almost identical to the graph of the function tangent hyperbolic. Let's ignore for a while the second picture. So we see that there is a density change on the interface, and therefore let's try to look up at the very simple experiment. We have a container with a liquid, and we immerse into it a frame built up from the wires, and the bottom wire in that frame is movable, and it can move up and down, and it has a length L, and it's very, very light. So we immersed that in the liquid, and then we took it out. Obviously, there is a sheet of liquid on that frame, and if there is just that very light wire, which, as I said, is movable, attached to the bottom of the construction, then this light wire will go up. So let's suspend from that wire, and the weight of that wire I denoted as a W1. because it's moving up, I want to stop it and have a situation where I have an equilibrium. So I suspend from the light wire a weight, with the weight denoted by W2. And properly adjusting that weight, I can easily get the situation where the wire is stationary. So then the force which is applied to the wire from the liquids is equal to the sum of these two weights. But if you look at the situation from a side, then we see that we have the wire. This is this bottom wire. And actually there are two layers of the liquid. It has two sides. So conventionally, that force divided by a unit length of the wire, L, is called a surface tension and is denoted by a small Greek letter gamma. So that force, which is balanced by these two weights, is equal to 2 times length times the gamma, and the gamma is a surface tension. The surface tension is a property of the liquid, and of course depends on various liquids, and it changes. And also, because all the properties of the liquid are temperature dependent, therefore the surface tension gamma is also temperature dependent. The units in which we measure surface tension are newtons per meter. All right, therefore, this is a table which shows you a values of the surface tension for different kinds of liquids and at different temperature measures in centigrades. So for example, for the liquids which we all know from everyday use, so to say, I'm talking about the disinfection of our hands and everything else due to the pandemic, is ethanol. And ethanol surface tension at the temperature of 20 centigrades is about 2 times 10 to the minus second newtons per meter. The oil, like the kitchen oil or the olive oil, has only slightly higher surface tension. It's also 10 to the minus second newtons per meter, but the coefficient is slightly larger. If we look at the water, then I have collected here the values of a surface tension for various temperatures at 0 centigrades, at 20 centigrades, and at 100 centigrades. And you see that the surface tension is lowered with increasing temperature, and we will come back to this point in a minute. Two last positions in my table are the oxygen and copper. Oxygen at the room temperature is of course gas, but when we cool it to the temperature something like the minus 193 Celsius, then it becomes a liquid, and then it of course has a surface tension, and the surface tension of a liquid oxygen is 1.57 times 10 to the minus second newtons per meter. Some of you might know that the oxygen was liquefied just before the liquefaction of the air. The liquefaction of the air was achieved for the first time by two chemists from the Jagiellonian University in Krakow, Wróblewski and Olszewski. And I'm talking to our foreign guests. If you will ever go to Krakow, I suggest you visit the Museum of Jagiellonian University. And if you really pay attention of what the guys are telling there, you might be able to go to the part of the museum where the original laboratory of Wróblewski is preserved. Wróblewski, and it is a kind of a dramatic experience to see the lab, because Wróblewski died during the experiments. He was experimenting at night, and this was winter, and he was alone in the laboratory, and he overturned the gas lamp, and the table caught fire, and the fire spread on the clothing of the Wróblewski, and he ran out of the building and tried to extinguish the fire by rolling in the snow, but that was ineffective, and he died from the burns. And that laboratory with half burned his lab papers and notes can be seen at the university, Jagiellonian University in Krakow. And the last position is a copper. Copper at the room temperature is a metal, but when we heat it up, it melts and it becomes a liquid. And the surface tension at the temperature, which is slightly above 1000 degrees Celsius, is, as you can see, a huge number, because it's 100 times larger than the surface tension for all the other substances in my tape. All right, so we have a certain feeling how strong is the surface tension, and I'm almost sure that in the high school you have done many experiments with the surface tension. For example, one of them is the floating of a needle on the surface of the water, and so forth. But I will come back for a second to this drawing, showing the density profile on the interface between liquid and its vapor. We discussed the density profile, but as you see, the density is a continuous function of the length S. If I don't look at the atomistic scale, then I can describe the density as a continuous function of a distance. And the interesting question is that this density changes very rapidly over the narrow region. And if I try to calculate the energy of the system, then it is obvious that I have split it into three parts. The one part is the energy of the liquid phase, because liquid is here homogeneous, so it has a certain energy contained in it. Up there is a homogeneous vapor phase, so it also has its own, so to say, energy. And then there is an addition term which comes out from this narrow interface. So the total energy of the liquid contains of the bulk energy, that these are these energies of a liquid and a gas phase, and also the energy in here. And it turns out that energy there in that interface, which for the first time was introduced into description of the physics of the liquid vapor, contacts of a liquid vapor by American physicist Joshua William Gibbs, the founding father of contemporary statistical physics, and many other branches of mathematical physics. Actually, Joshua Gibbs was the first professor of mathematical physics in the United States. He was a professor at University of Yale. And actually, what is also interesting, he was never paid for it. He was unpaid professor of mathematics at the Yale University. And there is an interesting story about it. So anyway, there is this addition contribution from the interface to the energy, and it has a form of the integral of a derivative of density with respect to the length of the Z. All right, so that's the interface. And let's continue to discuss that interface. Now I plot it horizontally, and the reason why I have plotted it horizontally is that we always are observing on the Earth the situation where the liquids are under the influence of a gravity. So the denser liquid is on the bottom of our vessel and the light liquid is on top. But what happens when there is no gravitation field? If we have the liquid which is not under the gravity. So it's not on the Earth, it's the liquid which is not on the moon, but we can do the experiment, for example, in the spaceship and in the International Station, which is circling the Earth, or in the shuttle, or in whatever. And what will be then the situation? How the system distinguish where is liquid and where is the vapor, whether it will keep the same structure. And that is very interesting question, which had been approached theoretically by many people, and we don't have time and also don't have a sufficient level of mathematics within that course to derive how that density profile between liquid and vapor depends on the value of a gravitation field. And this is a very, very beautiful part of theoretical physics. All right, so we have the density. Here is the gas, here is the liquid. And the interface has a certain thickness. And that thickness I have denoted by the quantity which I called psi. And for some reasons, I will call it correlation length or interface thickness. And I am particularly interested in what is happening with this gas-liquid interface when on this diagram, which we remember, we are looking at the properties of the interface between liquid and vapor, but very close to the critical point. As you remember, at the critical point, the difference between liquid and the vapor disappears, so to say. We are in a fluid phase where we cannot distinguish what is what. So the question is, what is happening when with that interface, liquid and vapor, when I'm approaching a critical point? At that critical point, the difference of a density between gas and liquid disappears. Therefore, what is happening? That curve must get flattened, which I can describe by also saying that when I'm approaching a critical point, this length, psi, a thickness of the interface increases, becomes larger and larger and larger. So I can write two expressions. One is the difference between the density of liquid and density of vapor, which I denoted as the delta rho, very close to the critical point, to the temperature of the critical point, when the pressure is constant. And that was a tremendous discovery in the 19th century, at the end of the 19th century, that difference is governed by the power law. There is a certain exponent, which I have denoted beta, which tell us how that density decreases when I'm coming close to the critical point. And at the end of the 19th century, Dutch physicist van der Waals had derived that expression, also showing that this is something like a tangent hyperbolic. And he derived the value of the exponent beta, and that the exponent beta, according to van der Waals, was equal to 1/2. But unfortunately, that is wrong. That value of the exponent was also measured by the experimental physicists, and the value of the beta was always different from 1/2. But I will tell you in a second what is the value. But the question is that this quantity, the difference of the densities in the liquid and the gas phase, tell us also in which phase we are, because it also changes sign when we cross this coexistence line on our phase diagram. So in some sense, this quantity delta rho tell us in which phase I am. If I will be dropped by a parachute on this area and I will just measure delta rho, then I will be able to say on which side of the border between liquid and vapor I have landed. All right, that kind of quantities which can tell me in which phase of the matter I do find myself is called order parameter. The name was proposed in the late 30s by the Russian physicist Landau, Lev Landau, one of the greatest physicists in 20th century. So the other equation which I can write here is that, as I said, that the psi increases. So when I'm approaching a critical point, this thickness psi, which is also a correlation length in some sense, is increasing. So it blows up. And it blows up also with a certain exponent, which is conventionally denoted by nu. And I have here a table with the values of those coefficients. The critical in these coefficients like this, beta and nu, are in the physics called critical indices. And the value of critical indices calculated classically is equal 1/2, but the experimental value is 0.34. And the nu classically might have a very different values, so I have not written it here, but experimentally is order of 1. So why I'm giving you these numbers? We are not going to talk about this, about the other phase transformations during our talks, but the theory of what is happening close to the critical points, which not only exist in the liquids, but also exist, for example, in the magnets. If you take a magnet and you've heat it up, then at a certain temperature, I mean, the magnet from the school, you remember, a little metal bar. When you start heating it, then at a certain temperature, it loses its magnetization properties. It becomes not magnetic anymore. So there is also the critical point for many other important properties of materials we use every day. And the science of phase transitions is one of the most important branches of theoretical physics. And it is remarkable that all those phase transformations can be, which happen in the different systems. They happen in the liquids, they happen in the magnets, they happen in the electrically active system like ferroelectrics and piezoelectrics and all sorts of other systems. This phase transitions, the physics of those phase transitions is, can be split into blocks of systems which, although have very different physical properties, they have very similar properties close to the critical point. And that is encoded in the fact that they are having the same critical exponents. And these critical exponents depend on a gross property of the system, and these gross properties are called symmetries and the range of the interaction. What are the molecular interaction in the system, and what are the symmetries of those systems? And it was a tremendous success of physics that the theory of the phase transitions was eventually brought into such a stage that the exponents, the experimental value of exponent, could be calculated from a theoretical models and becomes in agreement with the experimental values. The first step in that direction was done by Norwegian physicist Lars Onsager in the 40s, who solved a model of a magnetic system. And quite remarkably, he was able to solve that model when it was a two-dimensional, a flat surface with a lattice, and on these two-dimensional lattice points, a little magnets were sitting, and Onsager was able to calculate the free energy of that system and also show that at a certain temperature, the system becomes magnetized. Nobody ever solved that problem in 3 dimensions, but we have powerful computer systems which allows us to calculate the critical exponent. And what was remarkable that those critical exponents depend on the dimensionality of the system. In some sense, we learn from the critical exponent and the physics of phase transition that the dimension of the physical system, whether it's 3 dimension, 2 dimension, 1 dimension, is of a predominant importance. So that was a short comment on the phase transition, which conveniently could be slipped into our talk about the liquids. All right. So now we are going to talk for a second about the capillary waves. And this is another picture of a force which was applied, a concentrated force which was applied to the surface of a liquid, and we see those waves. If I have a wave, then the waves are having a wavelength, that is the distance between 2 consecutive crests of the wave, and the inverse, the wavelength in physics is usually denoted by like a Greek letter lambda. So there is another number which physicists call the wave number, k, which is just 2 pi over lambda. So if lambda is measured in meters, then k is measured in inverse of the meters. And the surface has a surface tension equal to gamma. So this problem can be solved, and the frequency of the waves, capillary waves, those waves on the surface, is proportional to its square is proportional to the cube of the inverse wavelength between the crest on this wave. And the coefficient in the front of it is the surface tension divided by a sum of the densities, where a rho is a density of a denser liquid, and rho prime is a density of the vapor. So this is an expression of a capillary wave on the surface of a liquid without the effect of a gravity. But when we solve the same problem on the surface of a liquid in the presence of a gravitation field, then we have a slightly different equation, namely the equation which looks like this. It has 2 terms. The first term, which depends linearly on the wave number, and the second term, which depends as a cube. We can easily see from analysis of that equation that there is a critical wavelength given by the square root of a gamma divided by difference of the densities, and because the square root cannot be taken from the negative numbers, then I put here the absolute value. And for lengths which are shorter, which are shorter, considerably shorter than this length lambda crit, this first term is unimportant, and we regain from that formula the normal surface tension. And in other words, for a short wavelengths, the presence of a gravity is of no importance. But if the lengths lambda are larger than that critical number, then the second term can be dropped, and we only have on the surface of a liquid a waves with which square of a frequency depends linearly of the wave number, and that kind of waves, without this second term, are called the gravity waves. Do not confuse it with the gravitational waves in the space. They are experimentally easily observed waves on the surface of a sea, and they have they are only there at the very long wavelengths. The problem is what is happening with the real waves on the real ocean when the length becomes very, very, very large. And then the problem is when the length of those wavelengths, when the wavelength of those waves becomes comparable to the thickness of the water on which they are propagating. The problem of the waves on a finite thickness ocean is of a tremendous importance. It's described by another equation, which I'm not going to write for you. It was discovered by the Dutch physicists, by two Dutch physicists, Korteweg and de Vries, and it's called Korteweg-de Vries equation. And that equation has a peculiar property that at a certain wavelength, the solutions of that equation become a huge wave, a very, very huge wave, which height is proportional to the velocity with which it's moving, and it doesn't change shape. It moves on the surface of the water or of the ocean without changing its shape, with a tremendous speed and a tremendous height. That wave in physics is called soliton, and in the Japanese language, it's called tsunami. And these dramatic events like a tsunami caused by the objects falling in the ocean or by the earthquakes are very well known from our experimental life. So that is the capillary wave, and a capillary wave play a very important role in processes which are, for example, boiling of water, boiling of a liquid. And about that we will be talking in our part of the lectures devoted to the science of heat. All right, so let's go on further. And I would like to bring you another important property of the surfaces of the liquid. And those properties they go under the name of wetting. Imagine we have a very common in everyday life situation that we have a solid surface and we put a drop of liquid on that surface. For example, as on the picture above. As we know, that drop will have, if we put the liquid on the surface of a solid, then it forms a drop. And let's focus our attention on what is happening at the edge of that drop. At the edge of that drop, we have three surface tensions which play the role. The one is our conventional surface tension between liquid and vapor and the gas, and that is denoted by the gamma LV. The other is a property is a surface tension on the interface between liquid and the solid. And I denoted it as a gamma S, solid liquid. And the third is something we usually tend to neglect. It's the interface between the vapor and the solid, and that is denoted by gamma S and V. And at the edge of the drop, when it's stationary, we have a balance of these three vector forces. And it is obvious that the values, relative values of these three forces determine that angle, which is formed by the line which is tangent to the surface of the liquid at that edge. That angle theta is called the wetting angle. And this is a kind of a triangular drawing of that what is happening. And this is a general formula. And it turns out, these are the definitions of these quantities, that when this angle theta is larger than pi half, that is larger than 90 degrees, then this is called, the situation is called drying. Well, why it is drying? Because if that angle is larger than 90 degrees, then this tangent is in that direction, and that means that the drop has a cusp here, not at the edge. So the liquid drop sits on the surface and tries not to touch it. When we have a situation like this, that is a situation which is used by the people selling us detergents for wash machines, because they change the surface tension such that the liquid changes, that the interfacial tension between the liquid with the detergent and the dirt, which is on the surface of our clothing, becomes larger than pi half, and the liquid goes underneath, so to say, a drop of dirt, and the dirt is free and falls off from our clothes, and that is also increased by the fact that the clothes are moving in the interface, so it is easier to shake the dirt from it. So that is the drying phenomenon. When the angle theta is less than pi half, less than 90 degrees, then the tangent line is in that direction. That is called partial wetting. And when the angle is equal to 0, then we have a complete wetting, because if that angle is equal to 0, then there is no drop, but the liquid forms a thin layer on the surface of the solid. And that remarkable thing about this three phenomena is that they also belong to the class of the phase transition. The situation where that situation, what happens to the liquids on the surface of a solid, is actually also, it is possible to describe it using the language of the phase transformation. And that was observed by the American chemist and metallurgist John Kahn, not that long time ago. Okay, so the important equation which governs that situation, what is actually happening and what is this drop doing, whether it is drying or whether it dries the surface, whether it partially wets the surface or wets the surface, is given by a relatively simple equation, which is called the Young equation. And this is the relation between the surface tension. There are three surface tensions and the angle theta, and they are related by the following equation. So that is the Young equation, and I will use now that equation to describe a phenomenon which is very important in biology, namely the meniscus. The meniscus is something relatively well known from everyday life. We observe it in glass of tea, for example. And this is a container which we fill up with the liquid. And I'm drawing here for a meniscus which is of that shape. There's a possibility the meniscus will be also concave. This is the meniscus. The height of the liquid is denoted by H. And on the edge of the solid and the liquid in the container, we have a balance of our forces. And the balance of the surface tension forces must obey the Young equation. So let's concentrate on equation Fg, which is the vertical equation, the force acting on the edge of the surface of the liquid touching the surface of the solid. And from the Young equation, we easily find that this force per unit acting on the length, I mean, this is a cylindrical container, therefore the length of the perimeter on that here is simply 2 pi r, and there is a surface tension solid liquid, and times the cosine of theta. And the weight of the liquid is the volume of the liquid times density times the gravitational acceleration. So it is easy to see that this is rho times g times pi times r squared times h. And therefore, at equilibrium, the force by a surface tension, so to say, pulling the liquid up the container and its weight which pull it down must be equal. So from that simple equation, it comes out that the height of the liquid in the cylindrical container on which it will climb in a cylindrical container in the presence of a gravitational field is 2 times the surface tension between the solid and liquid times the cosine theta and the rho gr. And that equation is called the Urey height equation. And that is equation which tells us how high can liquid climb within the stem of the flower in our flower pot. The flowers and vegetables have a tiny little pipes inside through which the water carrying the nutrition climbs up, and the Urey equation gives us that particular height. The last gimmick with the surface tension I would like to show you is called the Laplace law. And we imagine you have a container with the liquid and you are sitting on a space station and you open up the container and let the liquid go. There is no gravitational field. So the only phenomenon which can distinguish between liquid and the vapor is a surface tension. So there is no gravitational field which will tell me that the liquid has to be on the one side of the interface and the vapor on the other. But there is an interfacial tension, and the size of a droplet of the liquid released from the container in a spaceship will form a droplet, a spherical object. And there are beautiful experiments done by the astronauts in the space, which they have put up all sorts of liquids into the cabin, and these liquids form a blob, a spherical blob, which moves beautifully within the space shuttle. These are not exactly spheres in space, because the spaceship is not actually the object with no gravitational field, because it wobbles around, and therefore there are centrifugal forces in it. So this drop of the liquid released from the container in the spaceship is under the influence of a, to a large extent, random gravitational field, effective gravitational field stemming from the rotation of a capsule, a random rotation of a capsule. So the liquids form a sphere. So I will now be asking the following question. I'm having a container, like a rubber balloon, which I fill up with the liquid. And what is the pressure of the liquid on this on a rubber band which forms the wall of the balloon is called the tension. And what is the tension is an analog of a surface tension on the surface of the liquid and its vapor. So how is that tension or a surface tension in a sphere related to its radius? So I have to do this, to find out what is that value, I take my sphere and I cut it in half. I do the Gedanken experiment, a mental experiment. I cut the liquid drop in half, and there is this half of the droplet, which, as projected on a flat surface, there is the area of a circle here, pi r square, a proportion to pi r square, and the surface tension, which unfortunately on the drawing, which I copy from my textbook, is sigma, was denoted by sigma. It was too late to change the notation for the surface tension from gamma to sigma. So I apologize that on this slide, a sigma denotes the surface tension. And I have a pressure on that surface, so I can easily calculate the following relation, that the difference of the pressure from outside and inside of the sphere times the surface of the sphere must be equal to the surface of the effect of a force acting on the rim of that cut, and the rim of that cut is 2 pi r times the surface tension. So that is my relation between the change of a pressure outside and inside of the liquid drop to its surface tension, and that is called the Laplace law. So the out pressure minus in pressure is inversely proportional to the de radius, and it is proportional to the surface tension. So that is an equation which tells us that if I have a liquid at the pressure P in, then I can have very easily calculate what will be the size of that droplet. And that the same equation can be used to describe object which are not only cylindrical. So let's imagine a pipe, a cylindrical object. Then in the cylindrical object, I have obviously two kinds of a pressure, a radial pressure and this the pressure along the surface. And that is the relation. And the tension pressure, which I denoted by letter T and those arrows, is a pressure times the radius. And for a spherical, is a pressure is a half of it. And that is, this is very interesting equation. And you might tomorrow morning do the experiment with it at home. If you take a Frankfurter and you boil yourself a Frankfurter for a breakfast. If you take a Frankfurter, it is basically a cylinder, which, well, I'm not trying even to tell you what is inside, but whatever is inside of your Frankfurter, it's basically water, because a meat or whatever they use for production of a Frankfurters contains is essentially water. So the Frankfurter is a cylindrical object full of water. And when we boil it, then we boil the water inside of the Frankfurter and outside. But inside of it, it is under the different pressure that outside, because the liquid inside is held by the skin of the Frankfurter, that is a tension in the wall of the container. And at a certain, when we overboil a Frankfurter, when we increase the temperature of the water to it becomes much higher than is necessary, then the pressure inside of the Frankfurter increases. And in the Frankfurters at the end has almost spherical ends, and in the middle is a cylinder. So the tension in the middle on the skin of a Frankfurter is twice the tension at the end of the cylinder. So any material out of which the skin of the Frankfurter is made is having an elastic properties, and those elastic properties are characterized by a constant which is called the Hooke constant. And it's the same at the end of the Frankfurter as in the middle. So when we overcook the Frankfurter, then the tension in the T, this on the cylindrical side, is twice as that on the end. So when you exceed the elastic properties of the Frankfurter, it will break along its length. So you can do that experiment tomorrow, and you will find that always a cylindrical Frankfurter will always break along its length. And that is why when you grill the sausage, when you will be finally permitted to do some grilling during the vacation time, and due to this, when these restrictions will be lifted, then if you go to the grill and you grill the sausage, then take a knife before you grill it and make a slight cuts perpendicular to the length of the sausage, and then it will never break during the, even if you will over grill the sausage, because you will relieve the tension T and it will then not grow. This phenomenon is also the phenomenon which had been responsible for tremendously dangerous accidents of the ships on the Mississippi River. These famous Mississippi River boats have a pressure vessel for producing steam, for the steam engines, which were along the boat. So when they blow up, the whole boat exploded immediately. That you can learn from the Mark Twain book. So that is a Laplace law. And we will be now talking about the non-Newtonian fluids. What are the non-Newtonian fluids? We were talking about and let me first show you a film. This is a short film. I have no idea why the computer is showing it slightly shifted. I tried several times to shift it, but this is a container filled up with the liquid, which is a corn starch mixed with the water. It's a liquid, as it's shown in this experiment. And as you have seen before, it behaves like elastic balls. Now we have a vibration, and as you see, it vibrates like a membrane, because there are low frequency vibrations, so the wavelengths are, if the frequency becomes higher, it starts to develop droplets like a liquid. So there is a liquid which has elastic properties and liquid properties depending on how fast you are exciting it. Those gentlemen jump, so this is a very high frequency excitation. But now this is a low frequency excitation, and he drones into the liquid as it was a water. as you remember, we were discussed. So we have a certain liquid which has either liquid property or elastic property, depending on the frequency of excitation. And as you remember, when we were talking about the viscosity, we had this simple drawing, and the friction, the viscosity coefficient, was determined as a relation between the force applied to the surface of the liquid, the area, and the difference of the velocity along the y direction. This kind of expression, change of the velocity along the line, is called a rate of deformation. So that was a viscosity definition. But there are materials which are called non-Newtonian liquids, for which the same relation is not so simple. It's not linear. There is a certain function which relates that force to the rate of deformation. And the materials for which this relation does not apply are called non-Newtonian liquids. And here I have shown you a few, the relation. This rate of deformation is I denoted by epsilon to dot. This is some convention. This is the force. So this is our normal water and most of our Newtonian liquids. But when the force goes on linearly, but then becomes saturated, it's called a pseudoplastic. If it increases, it's called dilatation. And if it starts with a certain value, they are called Bingham pseudoplastic. It turns out that these liquids pay a particular property in our life because a human blood, and actually the blood of all animals, is to some extent the Bingham pseudoplastic. Here I have a certain table which shows the non-Newtonian fluids, and they are generally three-type. Shear thickening dilatant fluid, and apparent viscosity of those liquids increases with increased stresses. And example is that what was shown in the movie. There's a suspension of corn starch in water. It's called oobleck. There are shear tightening, pseudoplastic, where apparent viscosity decreases with increasing strain. And there are a whole list of them: nail polish, whipped cream, ketchup, molasses, syrups, paper pulp in water, latex paint, ice, blood, some silicone oils, some silicone coatings, and sand in water. And there are generalized Newtonian fluid, where a viscosity is constant, and example of them are plasmas and custard in water. So we are mostly interested in the shear tightening pseudoplastic non-Newtonian liquids because the blood is one of them. And, well, I'm sorry. All right. I would like to show you now the some effects related to the property of the non-Newtonian fluids. And this is the effect, which is called the Weissenberg effect. And that is just to show you that there are very recent works along the topic. And I have to play it. All right. And that is what is the Weissenberg effect. On the left, on the left side, you have a container. Container is filled up with the non-Newtonian tightening liquid. For example, a cream, sour cream is that substance. And we put a rotating shaft into the middle of it. and we rotate it very fast. Usually when we rotate it, you will expect that on the shaft there is a meniscus downward. But when you start rotating it very fast, you first find out that meniscus inverts itself and it becomes upward meniscus. So the liquid is higher up on the shaft than on the walls. And eventually, when you rotate it truly very fast, then it blows up along the line upward. I actually had, without knowledge of the Weissenberg effect, discovered the Weissenberg effect years ago when we had the dramatic period of history called martial law in this country. And there was a shortage of everything, including a shortage of butter. But the cream was available on the farmer's market. So I went to the farmer's market, bought the cream, and decided that I will make butter at home. So I put it in a glass, and of course I didn't have a proper butter making devices. So I just used a mixer, put the rotating shaft in the middle, switch it, and it was going on and nothing was happening. So I increased the speed of the rotation, and bingo, the Weissenberg effect happens, and the whole cream out of the container end up on the top of my, on the roof of my kitchen. And I'm not going to tell you what my wife said when she saw the result of my pseudoscientific experiment with the non-Newtonian liquids. So this is a Weissenberg effect, and Weissenberg effect is very often used in switching devices. We have a conducting liquid which is rotated. There is a shaft, and under the certain when the rotation exceeds a certain speed, then the conducting liquid rises over the shaft, touches the upper electrode, and the circuit is switched on. And of course, the same way the circuits can be switched off. So there are thousands of uses of this rotation. But here I would like to show you the almost the last slide of that part. This is a drawing which shows you some properties of our blood. On the left side, you see the relation between this flow speed and the pressure. And this is a drawing for a water. Forget this number NR. That's from some other story. So we have the relation which is linear. But when we increase when we have a blood, when we have to exceed a certain value of a pressure to force the blood to move in our veins. So that is why it is a Bingham fluid, because you have to apply a certain force before it starts to moving, and then it actually moves almost like a water, but then there is a considerable difference in the value of the viscosity coefficient. The other property of the blood is that the relative viscosity depends on a parameter which is called the hematocrit. Hematocrit is a concentration of red blood cells in a total volume of the liquid. And as you see, the viscosity increases with in a non-linear fashion with the change of hematocrit. And that is pretty important, because that viscosity determines how the liquid gets into the capillary veins, which deliver nutrition to the essentially every cell of our body. So we have learned over last several lectures of basic properties of the liquids. and we have seen that they are applicable to the many problems from the biology. But as you might remember, we have started our discussions by talking about the allometry, the laws which relate the various properties of the body of biological species to their mass. And you might remember this relation, which was written in red here, which was called allometry law, which said that those relations were usually a power law. And I have shown you that the mass of the eggs of the birds is related to the mass of the body of the birds by universal exponent, which was 3/4, and also that the mass of the human brain was proportional to the mass of a human body with the exponent 3/4. And there were arguments provided by West, Brown, and Nenckigo back in 1997 that this is a universal law of physics. And I would like to close our meetings about the fluid dynamics by a derivation in quotation mark of that relation, where I will use basically those laws of hydrodynamics I picked up for our lectures. In particular, I will use the properties of a viscous liquids and the Poiseuille flow, which will turn out to be important in derivation of that law. So I'm sorry, something is confusing here. You remember, the problem is that we know that the nutrition rate, the quantity which tells us how much energy we have to deliver to our body in order to keep it going, is proportional with some exponent to the mass of the body. And the nutrition, be it blood, oxygen, or whatever, is delivered to the cells of our biological system through the network of carriers which carry that nutrition. And I will be considering that nutrition to be a liquid, a viscous liquid, and the network is something which I show it here, and for the mammals it's a blood system. And we know that this the same is for the plants. The plants have these tiny little pipes, so to say, inside, which carry the liquid with the proper solution of nutrition ingredients to the upper parts of the plant. And this looks also very similar. And experimental shows that those networks are growing in a very self-similar system, that if I look it up at each of those parts of that network, and well, if I look here, it splits in 3 parts, but if I cut it here, then it also goes and splits in 3 parts, and so forth and so forth and so forth. So on each level of the expansion of the network tree, it looks identical. So actually, I have the main zero order part of my network, the huge aorta in my body, which splits into layers of the system, and each of those layers I envisage as a tiny pipe through which a flow goes according to the Poiseuille law. Well, the blood is liquid, which is viscous. When it starts flowing, we can to some extent forget that it's not Newtonian. And therefore, when it's already going, I can apply a Poiseuille law. So I know that the rate of flow of the liquid through that pipe is proportional to the area of the pipe and PRK squared, and times the average velocity of the liquid with the nutrition of the blood in that pipe. So I build up the model, and now I will systematically use a certain fundamental assumption. The first is that the amount of fluid is conserved. Whatever comes into the zero order layer of our network goes on there and it's not lost. So let's now do some more mathematics. Each of the tubes in my system branches into k new ones, and a number of those pipes on the level k I label as nk. So at the level k, for example here, the total number of the branches is a product of the numbers from the first zero level to the level k. So in the zero level, there was N0 pipes. On the level 1, there was N1, and the level k is the number k. So the total number of branches is capital N, which is a product of those. So because of the conservation of the flow, then the rate of flow Q0 on the level 0 is the same as at the level k. So it must be the flow at the level k times the number of tubes at the level k. Okay, so keep the level n sub k here, but qk is a area on the tube on the level k times average value u. So the same goes on, goes on, goes on, and eventually it ends up. It ends up in a capillary. Tiny capillary veins which supply essentially all the individual regions of our body, and this must be the same. So the same formula holds for the last layer in my network, where the total number of tubes is n sub c from capillary, and this is the area of a capillary times velocity in the capillary. Because the flow in the zero layer of my network is essentially proportional to the metabolic rate, then I have a relation between the metabolic rate and the number of tubes in the capillary layer. And because the B is proportional to the mass of the living system with an exponent A, this formula gives me a relation between the mass exponent A and the flow of the nutrition. Now, the capillary sizes are in size invariant. What means the size invariance? That means that the radius of a capillary vein, the length of the capillary vein, velocity, average velocity in it, and the pressure drop on that pipe, capillary pipe, are independent of the size of the animal or the tree or the living object. So if I make this assumption, then because the metabolic rate is proportional with exponent A to the mass, then the flow at the zero level of my network is proportional to the mass with exponent A. And from that equation, Q on the top, the number of tubes in a capillary layer is also proportional to the mass with exponent A. So now I have to use another argument, namely that the energy is lost in the system layer by layer. The energy is conserved. If that is happening, then there is a complication mathematical calculation, which I will skip at that moment, which allows me to make the following conclusion. If I scale the radiuses of the tubes at the level k, namely if I introduce a dimensionless number beta k, which is a ratio of the rate of the radiuses at the level k plus 1 and the radius k, and the gamma sub k, which is a ratio of the lengths, and the nu k, which is a ratio of the numbers of at the level k plus 1 and the neighborhood, then this three dimensionless numbers are actually constant. That is a conservation energy consequence. And I hesitated a long time whether I should prove it or not in details, but that's a lengthy calculation, and which is, you have to trust me to some extent at least. And out of that conclusions, we see that we have three numbers, beta, gamma, and since eta k plus 1 divided by nk is equal to 1, then nk is equal to some number n. And there are and now we will be discussing the properties of our network, which is the self-similar fractal. Since the number of the capillary of tubes on the capillary level is increasing with the geometrical proportion, we have showed it on the previous slides, then the total number of the tubes in the capillary level is this constant n to the power capital N, where the capital N is the number of tubes in the total system. Since the capillary number of tubes in the capillary layer is proportional to the mass with the exponent A, then, I mean, it's proportional, but they are different by the dimensions. This is a number, and the mass is measured in kilograms. So I cannot write the equation equating apples and peaches. I have to, therefore, write a formula which says that the number of tubes at the capillary level must be equal to the mass, but there must be a unit of mass, which makes this mass dimensionless. So this is m divided by this unknown to me at the moment, mass m0, with the exponent a. If that is happening, then from this formula it follows that n to the power capital N is m to the power a, and therefore the exponent a is related to the very simple formula where I use the natural logarithms because I prefer to work with exponent, not with the numbers, so I have the very simple expression. Well, that expression is remarkable because it tells me that the in the living systems, there is a difference between the number of layers and number of branchings and the weights, a ratio of weights. So for example, if I compare the mass of a mice to the mass of the whale, which is of the order of a 10 to the minus 7, then there is only 70% more branching between the aorta and capillary in the whale than in the mice. So this logarithmic relation makes all the animals already somewhat similar. That is actually why we prefer to use logarithms, because logarithms are essentially of the same order, so we can compare the logs. I mean, you must be told on the lectures on statistics why in many histograms in biology and medicine and in economy, it is worthwhile to plot the histograms not for the variables, but for the logs of the variables, because then we compare large and small numbers, which is not usually very convenient. All right. I believe we are approaching the end of my lecture, so we will be having a brief reassumption of what I said next week, and we will next week, let me immediately flash you. Oh my goodness. I will be coming to this. I want to get to the. Next week, we will start part of our lectures, which will be called the kind of motion we call heat, which is the title of a beautiful book by Stephen Brush about the science of heat. And we will start with a short history, which relates the science of heat to the biology. So thanks for today.